If you just hopped on, hi. We're going to get started in a minute. For now, I would just make sure you have a phone or a device nearby where you can shoot me remind messages. And we'll get started in a second. Again, if you just hopped on, we will be up and running in a second. We are just giving everybody another minute, and then we'll get started. At any point, feel free to either send me a remind or just chat in the YouTube chat box. Both work for me, and I can see your message either way, so it's totally up to you what you would prefer. We're going to get started in about 1 more minute. Okay, so here's the deal, guys. We're going to get started at any time. If you have a question, just shoot it to me on Remind, or you can chat right in the YouTube chat box. You just need to be logged in your YouTube account to do that, okay? This is your review, so ask as many questions as you need to. And we're going to go through your 3 major topics, go through some examples, and then we'll be done for the night. So if you are giving up this to watch the end of the Duke game, or if you're giving up the end of the Duke game to watch this, I'm impressed. One thing to talk about quickly before we go on to anything else is how this grade is actually going to be calculated. So remember that 15% of this test grade is going to come from your lab, and the 85% will come from the actual tests you take tomorrow. So I am fully aware that this is a difficult test. This topic is usually the one where people struggle the most. It's all applications. And so remember, A, that 15% is coming from your lab, and B, that there will be some kind of a curve. So this is going to be one of those scenarios where you get in there and your goal is to just do your best. And as long as you do that, you are going to be totally fine as long as you've prepared. So we've got 3 topics. We've got optimization, which is finding maximums and minimums. We've got particle motion, which you guys were really, really, really strong at. And we've got related rates, which was that last topic that we talked about. So we're going to go through sort of in order of where I think we're struggling the most. And we're going to start with particle motion. So we're going to kind of breeze through this, just look at a couple things, see what we have difficulty with, and then we'll go from there. So starting with particle motion, the 2 things I would caution you is if you're talking about velocity and acceleration, don't just call them V and A, right? Let's say you're given a position function X. You need to make sure, like in this example, that you call the velocity function X prime, and you call the acceleration function X double prime. So you can't just go saying V because, again, this is not a physics class. We are looking at the calculus of it. And so you've got to make sure you define what your variables represent here. So we're going to look at a couple. We're going to kind of skip around here. But let's say we're given particle moving along an x-axis. So that just means moving left to right or right to left. And time is greater than 0. So that's defined there. We're not talking about negative time. Where this is my position function. At what time is the particle at rest? So what I want you to think to yourself is this asking me about position, velocity, or acceleration? In this case, this is asking me about the velocity because I will be at rest when my velocity is 0. So in this case, what that means is when x prime is 0. So what I'm going to do is find the velocity, set it equal to 0, and solve. So this is my position. Velocity will be the first derivative of that. So that will be 6t minus t squared minus 30t plus 36. So that's my velocity function. If you really desperately want to use v of t here, throw that out front and then you can define it that way. Now we want to see where this equals 0. We are really looking for critical points here, but we're going to find where that velocity is 0. And it's quadratic, so I can factor out a 6. I'm left with t squared minus 5t plus 6. This is factorable, so t minus 3, t minus 2. And so I get that my zeros are at 3 and at 2. So those two times would be the times when the particle is at rest. Now, when is the same particle moving right? Well, that is going to mean that I'm looking for where my velocity is positive. Because if we're moving along an x-axis, moving to the right we would define as positive, moving to the left we would define as negative. So what I'm looking for here is when will that velocity be positive? So I'm going to start with, well, when is my velocity 0? And that's at 2 and at 3. And then I'm going to think about my signs, and I'm going to do sign analysis on the velocity function because I'm not worried about where its position is negative. I'm worried about where its velocity is negative, right? So looking at my velocity function, this is a quadratic. It's a positive quadratic. So I know it's going to go like that, positive, negative, positive. You can also just plug in and check values. But here, this would be from 0 to 2 and from 3 to infinity. And I would be ready to explain that, right? Because x prime of t is greater than 0 on those intervals, right? Or you could say v of t as long as you defined it there. All right, continue to send questions if you guys have them. So let's look at this one. So a particle travels horizontally, so its position at any time is given by x of t equals that. Find the acceleration or the position when the acceleration is 1. So this is one where we've got the same dynamics, the same sort of material, but we've got more information in here. So I'm looking for position. So that means ultimately for my final answer, I'm plugging into that function. But I want to know when the acceleration is -1. So let's look at the acceleration function. So the velocity function would be this. Now, remember that 3t over pi is really just 3 pi times t. So the derivative of that is 3 over pi. The derivative of cosine is negative sine. So that right there is my velocity function. Now my acceleration function, I would take the second derivative of that. And this would just be 0, because that's a constant, minus cosine of t. So my velocity function we had up there, and now my acceleration function is just negative cosine of t. So I'm looking for where this equals -1, and that will give me the time that I want to plug in. So I'm really looking for where does cosine of t equal +1, right? We're looking for that place. Now look at my interval. It's saying from pi over 2 to 5 pi over 2. So let's think about our unit circle. Cosine is 1 when the x value is 1. So cosine is only 1 over here at 0 degrees. And so in that interval, well, pi over 2 is here. Pi over 2 is here. There's pi. So at 2 pi, right, t would equal 2 pi. And then 3 pi would be here. 4 pi would be back around. And that is past 5 pi over 2. So actually, we are good with just 2 pi because that's 2.5 pi. So that's my t value. So now what I'm looking for is what was the position at that time. So I'm going to plug that back in to x. So that's 3 times 2 pi over pi plus cosine of 2 pi. Those cancel, so this is 6 plus 1. So my position was 7. All right, let's look at one more particle motion, and then we're going to move on to some related rates and optimization. So on what intervals is the particle speeding up if this is a graph of velocity? Now, speeding up means that we need our velocity and our acceleration to have the same sign. They can both be positive or they can both be negative. So here's what I would tell you to do. I would tell you here to create a velocity and an acceleration sign chart. And notice what we've got here is v and v prime. So looking at that, let's start with velocity. When is velocity positive? When is velocity negative? This is a graph of velocity. So velocity is positive anywhere that we are above the x-axis. So that changes signs at 6. And when I mark that, I'm going to mark 6 on both of these because that's going to be important to me later. So at 6, and it can be helpful sometimes to like dotted line that down, right? So to the left of that velocity is positive, to the right of it, it's negative. Now, let's look at acceleration, and remember that that's the slope of velocity. So there is a positive slope from 0 to 2.
Duke lost.
Duke lost?
Yeah.
Oh my God, that's amazing.
Yeah.
That's awesome. So 0 to 2, we have a positive slope. 2 to 4, we have a negative slope. So again, I'm just marking those up. And then from 4 to 5, we have 0 slope here. 5 to 6 is again negative, and that goes until 7. And then 7 to 8, we are positive. So I'm really breaking this up and looking at what are the signs here. Now, on this velocity one, it's still positive there. It's still positive here. It's still positive there. It's still positive there. And then, I'm sorry, at 6, it switches signs. So it goes negative at 6, negative. So now let's look at where these match up. So I'm going to have positive, positive here. I have positive, negative there, positive, 0 there, positive, negative there. So I don't want those. Now here I have negative, negative. And that's all I've got. So this is going to be from 0 to 2, where I am positive and increasing. And 6 to 7, where I am negative and decreasing. Be careful. Do not just say it's, it's speeding up because acceleration is positive. So that's what I would be careful of. Okay, that was all I really had for particle motion. I think you guys have been doing really well on that. So I'm going to give you about 30 seconds, and then we'll go into some optimization. But take 30 seconds, send me any more particle motion questions that you have, and we'll go from there. All right, I'm not seeing any, so we are going to go on to optimization. Okay, so here's the deal with optimization. The key is writing an equation of what you are trying to optimize and what your constraints are. That's really your key here. If you can do that, everything else is usually pretty easy calculus. Now, formulas I expect you to know. Pythagorean Theorem, basic trigonometry, area of a parallelogram, area of a circle or area of a triangle, and volumes of prisms and cylinders. Any sort of shape where it's just area of the base times the height. So what we're going to go through here is we're going to go through practicing some writing constraints and writing what you're trying to optimize. We will do 1 or 2 where we do the calculus all the way out. But again, once we get it set up, that's usually the easier part. So I want to work on the setups here. So let's start with an easy one. So find 2 positive numbers such that their product is 192 and the sum of the first plus 3 times the second is a minimum. So I'm going to start with, well, what am I trying to optimize? So I see that word minimum, and that's a clue to me. And I see the minimum is the sum of the first and 3 times the second. So I'm going to say, okay, the first and 3 times the second. That's what I want to minimize. So I'm just going to call that M. It doesn't matter what you call it. But that's what I'm trying to minimize. Now, what is my constraint? Well, I know they're positive. I'm not going to write an equation for that, but I know that. And their product is 192. So I know that x, y is 192. So now at least I've got this, right? So let's see what we can do here. So you can solve your constraint for either one of the variables. Doesn't matter x or y. I'm going to solve for, let's do x. So this would be 192 over y. And then I'm going to plug that into what I'm trying to optimize. So here I would have m equals 192 over y plus 3y. And remember, it can often be helpful in calculus to rewrite this as 192y to the negative first plus 3y to the first. And so that is what I'm going to actually take a derivative of. Because when you're trying to find a minimum, remember, you're looking to come up with a sign chart and find where you're going. Your derivative is going from negative to positive. That will give you a minimum. So there is my function. So taking a derivative of that, and I'm just going to shrink some stuff down here so we have a little more space. So taking a derivative of that function, we are going to have negative 192 y to the negative second plus 3, right? and I want to see where that equals 0, and then I want to go from there. Now, my advice to you when you have something like this, when it's confusing for you to have, negative exponents and should I factor them, would be to just move one of the terms to the other side, right? That will make it a little bit easier. And so now you really have negative 192 over y squared equals negative 3 over 1. And you can cross multiply here. So you can say 3y squared, negative 3y squared equals negative 192. Divide both sides by negative 3. So 192 divided by 3 is 64. And so y equals plus or minus 8. Now, you have to think about your other constraint, right? Your other constraint was that they should be positive. So here you're getting that y should be 8. And then plug x back in there. So plug x back in because you know that x times y is 192. So 192 divided by 8 is 24. And that would be my two numbers. Now, if they ask you for the product, you could then just multiply those. So that is the basics, right? Find the derivative, set it equal to 0, and you should be checking that it goes from negative to positive there. So let's look at some more setups because I know typically what we struggle with is not the calculus, it's normally the setup, right? So let's look at some setups and see what's going on here. So a 540 square foot field is surrounded and divided into 3 equal parts by a fence. So let's draw what we know. Divided into 3 equal parts by a fence. Find the minimum amount of fencing. So it's asking me for a minimum of the perimeter, right? And we know the square feet, so that is an area. So let's see what we know. I'm going to define this whole side as x and this side as y. And so the area is our constraint, and so that's 540 equals x times y. Now, amount of fence, the thing we're trying to optimize or minimize is, let's see, well, I know those two sides would be x. Each one of these are y. So 2x plus 4y equals what I'm trying to minimize. And remember that, you can draw these pictures. If you're trying to do this without drawing the picture, it's going to be bad all around. But if you draw the picture, it will make it a lot easier. So this was my constraint. This is what I'm trying to optimize, so I'm going to plug into that. Again, it doesn't matter which equation you pick. I'm going to solve for, maybe we'll solve for y this time. So y equals 540 over x. So I would get 2x plus 4 times 540 over x equals m. And again, simplify, so m equals 2x. 540 times 4 would be 2160. X to the negative first. And then you're going to do the same thing. So find m prime, set m prime equal to 0, and then look for your minimum, which would be where you go from negative to positive. So again, I'm not going to spend a ton of time actually just taking the derivative, it's power rule, but I did want us to look at the setup. All right, let's look at this next one. A right triangle with a hypotenuse of 5 radical 3 inches is revolved around one of its legs to generate a cone. What is the volume of the cone? So, greatest possible volume. I am trying to maximize volume of a cone, which is 1/3 pi r squared h. I will give you that. You do not need that memorized, but it's 1/3 the volume of the cylinder that it would fit inside. Now, we know that the hypotenuse is 5 radical 3. So we're going to think about how we need that, but let's sort of draw a picture first. So I know that I have a right triangle that is spinning around, right? Spinning around there. And so that's going to give me this. And I want you to notice here that the radius of the cone is the radius, is one of the legs, right? And the height of the cone is the other leg. So that's what I'm working with there, right? I've got the radius and the height actually being the two legs of my right triangle. So think about how this 5 radical 3 might help us now. I see a right triangle there. And so what I see is that using Pythagorean Theorem, I could come up with that, right? R squared plus a squared is 5 radical 3 squared. It may help here, throw parentheses around that, to simplify this a little bit. So this would be 25 times 3, which would be 75. And so I can choose which variable I want to isolate. I'm going to solve for, let's solve for r. So solving for r here, I would get r equals the square root of 75 minus h squared, which, by the way, is not 75 minus h, okay? Not that. So be careful with that. I'm going to plug that in up here. So my volume formula is going to be 1/3 pi r squared h. This is the square root of 75 minus h squared. And so what I'm getting is that volume is 1/3 pi and then 75 minus h squared, because the square and the square root undo each other, times h. Now again, here, I think it would make your life easier to do some simplifying. So, okay, let's think about this. This is really 1/3 pi h times 75 minus h squared. And then what we can do is distribute this out. So 1/3 times 75 is 25 pi h minus 1/3 pi h cubed. And now again, you could do the same thing, take a derivative, set it equal to 0, and find, now we're looking for the maximum. So on your sign chart, you're looking for where you go from positive to negative. All right, let's set one more up of these, and then we're going to do some related rates. And you guys are super quiet tonight, so please send questions as you have them. But this last one we're going to look at is a distance problem. So we are going to find the point on the curve y equals radical x that is closest to the point 4, 0. So I'm always going to sketch this. Y equals radical x is 0, 0, 1, 1, 4, 2, and just keeps going like that, right? And I'm looking for the closest point to 4, 0. So I know that that point's 2 away, but the question is like, is there a point somewhere over here where maybe it might be a little bit closer, right? So that's what we're looking for. So I want you to think about this. This point we know is 4, 0. And this point I know is xy. And we can get a little bit more specific because our constraint here is that y is x squared. So what I really have is radical x. So now that's our constraint, right? That we have these points. What are we trying to optimize? Well, we are trying to find the closest point. So what we are trying to optimize is distance, and that is square root of x2 minus x1 squared plus y2 minus y1 squared. And so distance is the square root. Let's sub in our points, which would be this and that. So distance is, x minus 4 squared plus radical x minus 0 squared. And so that's what you're trying to optimize. Now, as we said before, usually it's easier to do some simplifying. So this would be x squared minus 8x plus 16 plus that right there is just x, square root of x squared. So you're really doing the derivative of, I'm going to write this all to the 1/2 instead of radical, x squared minus 7x plus 16. Now, let's actually do a derivative of this one because sometimes this trips people up. So d prime would be, this is chain rule because you have an inside and you have an outside, right? So derivative of the outside, you're going to take the derivative, leave the inside alone, times the derivative of the inside, which is just 2x minus 7. Now, I'm going to rewrite this just to make my life a little easier. So I've got 1/2, and then the negative 1/2 power is really this. And then the 2x minus 7 we could leave on the top. So all I did there was take this part and rewrite it as a radical in the denominator. So looking at this, I'm not looking for where the derivative is undefined because this is talking about a real quantity and we're not going to have this be undefined here. So really what I'm looking at is where the numerator equals 0. So 2x minus 7 equals 0. That means x equals 7 over 2. And I want the coordinate, right? Find the point So now I need y, so y would equal square root of 7 over 2. So my point here would be 7 over 2 radical 7 over 2. So what that means on my graph is that the point at 3.5 is actually the closest point to that. All right, I'm going to give you guys about 30 seconds and then we'll do some related rates and we'll go from there. So take a second, send me any questions. This is your moment. We're going to move on from optimization to some related rates. If we move on and you still have a question, please just send it, okay? Totally up to you. We can always go back or go, once we have a second, go back to something. All right, related rates. Remember with these, we're looking at how things change with respect to time, right? So you're always going to have this extra element, which is the idea that you're going to have like dr dt or dx dt, because every one of these is going to involve the chain rule and implicit differentiation. So the radius of a circle is changing at this rate. So I already know that that's dr dt, and it tells me that's positive, so I'm assuming this is increasing. At what rate in square inches per second is the area changing? So I'm looking for dA dt. And we know that at a point in time, r is 5. So it's not always 5, but it is 5 at one particular point in time. So what we need to come up with is a formula that will relate r and a together because we want to know how their rates are related. So I know area of a circle is pi r squared. So now we're going to take a derivative of this. There's only one variable, so I don't need quotient or product rule. So dA dt is going to be, pi is just a constant. Derivative of r is 2r, or of r squared. And we need to multiply by dr dt because we're taking the derivative with respect to time. And now all we need to do is plug in. So dA dt is pi, 2 times 5, and dr dt is 1 over pi. So nicely here, the pi's just cancel. And this is actually just increasing at 10 square inches per second. So that's sort of your easiest case scenario where you're just given the rates and the information you need. You don't need to solve for anything and you're good to go. So let's get a little more interesting and let's read this next one. So we're talking about a ladder, right? That is leaning along a wall. So an 8-foot ladder is leaning against a wall. The top of the ladder is sliding down the wall at a rate of 2 feet per second. How fast is the bottom moving along the ground at this point? So let's look. 8-foot ladder. That never changes. That's really important to remember. It's constantly that, which means the rate of change of that would be 0. Now the top of the ladder is sliding down the wall. So let's call this x. That's sliding down the wall at 2 feet per second. Because x is getting smaller, I'm going to say that that's actually -2 because it's decreasing. How fast is the bottom of the ladder moving along the ground? So let's call that y. So dy dt is what we're trying to find. At the point in time, so at a point in time, not always, I don't know why I wrote POT instead of PIT. Point in time when the ladder is 4 feet from the wall. So that's when y is 4. So let's see what we know and what we don't. So I'm going to start with, well, I want a way to relate x and y together. And the only thing I know that relates the sides of a right triangle is the Pythagorean Theorem. So I know that that's a squared plus b squared equals c squared. But in this case, the 8 is never changing, so I can actually plug that in right now. So x squared plus y squared equals 8 squared. So let's take a derivative. So 2x dx dt plus 2y dy dt equals, the derivative of 64 is really just 0. Now, let's see what we know. We know 2. We don't know x right now, but we do know dx dt. We know 2. We know y. We don't know dy dt. That's what we want. So that's my unknown. So I'm going to leave that. Which means to actually solve this problem, I need to figure out what x is, right? And that's where this point in time information becomes handy again. Because we know at that point in time that this was 4 and this was 8, and I don't know that side, right? So we can solve for that. So 4 squared plus x squared equals 8 squared. If you remember your special right triangles, you might even be able to do this without that. But this would be 16 plus x squared equals 64. So x squared would be 64 minus 16, which is 48. Yeah, 48. So x equals square root of 48, or you could get really fancy and say that that is 4 radical 3. Now, let's plug that in. So this would be square root of 48 or 4 radical 3. And so what you wind up here is negative 16 radical 3 plus 8 dy dt equals 0. You can move the 16 radical 3 over, so 8 dy dt equals positive 16 radical 3, and then divide both sides by 8. And you could reduce that to be 2 radical 3. And I want to throw units on that because they gave me units. So this would be feet per second. Okay, continue to send questions. We're going to do about 2 more, and then I am out of here. So continue to send questions as you have them. All right, let's look at this next one. The width of a rectangle is increasing at a rate of 2 centimeters per second, while the length increases at 3 centimeters per second. At what rate is the area increasing when W and L are those given lengths, 4 and 5? So, rectangle, right? Let's actually draw it. We have the width and the length. We know that dW dt is 2 and dL dt equals 3. And we want dA dt. And so here's what's a little complicated. We need a formula that will relate W, L, and A all together. So this needs to have 3 variables in it. At a point in time, we know that W is 4 and L is 5. So let's look at this. The formula that I can think of that relates those all together is LW, area equals LW. In this case, there are 2 different variables. So I cannot just be like, okay, ignore one, pretend it's constant. So to do this, I'm going to need to do product rule. dA dt is the first times the derivative of the second plus the second times the derivative of the first. Now, from there, I can plug in. So L is 5, dW dt is 2, W is 4, dL dt is 3. So this would be 10 plus 12. So this is increasing at 22, and its area, so centimeter squared per second. All right, we're going to look at one more, and then we are out of here, unless you guys have some questions. So in the figure above, a hot air balloon is rising straight up from the ground. It's tracked by a television camera 300 feet from the liftoff point. That does not change. That will probably be important, okay? At the moment when the camera's elevation is pi over 6, so that's at a point in time, the balloon is rising at a rate of 80 feet per minute. Now, rising, that is the change in its height. So dy dt equals 80 at the point when theta is pi over 6. I want d theta dt, what is the rate the angle is changing at that moment. So let's think this through. So what's a formula that I know that would relate theta to y? The only one I can think of here is a trig one. And since I know this is y, and I know that's always 300, I'm going to use tangent because we have the opposite and the adjacent. Now, there's 2 different ways you can think about this derivative. I'm going to show the easier one, and then we'll talk about the one that will, always get you the right answer. So when I look at this as somebody who's been doing this for a while, I break this up and think of this as 1 over 300 times y. And so when I take this derivative, I'm going to just take the derivative of each side. So the derivative of tangent theta is secant squared theta times d theta dt. And then this is just 1 over 300 dy dt. It makes it much, much easier. Now, if you don't think of that, here's what you need to do. You need to say, okay, derivative of tangent is secant squared theta d theta dt. equals, now the right side's a quotient, so it would be low d high minus high d low, square the bottom, and away we go. And you know what you got? Exactly what you got over there. So either of those are fine, and quotient rule will always get you the right answer. It's just the idea that perhaps it is not the fastest way to get there. So now we'd plug in. We'd say, okay, secant squared of pi over 6 d theta dt equals 1 over 300 times 80. Now, the 80 over the 300, I can deal with that. Getting secant of pi over 6. What I'm going to do is find cos pi over 6 and then flip it, right? Do 1 over that. So cos pi over 6, remember your chart, 1, 2, 3, 3, 2, 1, all over 2. So fun to draw. Square root the tops and sine and cosine. This is pi over 6, pi over 4, pi over 3. So cosine of pi over 6 is right here. It's radical 3 over 2. So here's what I'm going to do. I'm going to do cosine pi over 6 would be radical 3 over 2. So secant is 2 over radical 3. And then I need to square that. So that's 4 over 3. So this would be 4 thirds d theta dt equals 8 over 30, which, let's see, could I reduce that more? 8 over 30, 4 over 15. And then multiply both sides by the reciprocal. And so this would be 3 over 15 or 1/5. And your measurement there would be radians per second because we're talking about an angle. So this is 0.2 radians per second. All right, guys, that's all I have planned. So I'm going to hang out for about 2 minutes. If you have questions, let me know. Otherwise, I will see you guys tomorrow. I will be there early. So if you feel like coming in early, totally fine. I will be in my room. But let me know what questions you have. All right, we're going like 30 more seconds, guys. All right, it has been real. Let me know if you guys have other questions, and I hope you have a good night. See you later.